So why would you want to partition your data? Might be a dumb question, but it's worth thinking about. So when you have any sort of large data set, you don't want to have to process the entire data set each time there is any change. So like anytime there's new data or there's a change in your logic. So in almost all data engineering tools, you'll have some sort of partitioning that helps you control this. So you ultimately save on any processing or compute, and you ultimately save on money, which is what we care about. A couple of really important reasons, other than that, as to why we care about partitioning. One is performance. So when you partition your data, you're reducing the amount of data that's reprocessed at each step. So that means that you can actually have multiple partitions running in parallel. This is super helpful, as this helps our data pipelines run a lot faster. A lot of us have SLAs we need to meet, so time is key. Another great reason to partition is scalability. We're all in the industry of big data. So partitioning makes it so that your data pipelines are more scalable as you get bigger and bigger pipelines. Because when your data is separated into partitions, you can split that processing out over various nodes or whatever processing unit your compute engine is using. And finally, it makes it a lot easier to debug any issues you might be having in your pipeline. So let's say you have data quality checks that are failing, or you have any errors in your pipeline. When your data is partitioned, it makes it a lot easier to pinpoint where those issues are coming from. So let's briefly talk about what we're going to be digging into today. The first thing I'm going to cover is partitions within Ascend. Just generally, what are they? How do they work? Where to look in the UI to actually understand what they're doing. And then we're going to take a little trip down your pipeline to understand, how does partitioning work in ingest? How does repartitioning your data work in your transforms when you're actually transforming your data? How can you manipulate that to best meet your use cases? And then finally, we're going to be taking a look at a couple of use cases about how Ascend manages partitions when writing data out. This is going to be interesting. It depends on write connector to write connector, but understanding those fundamentals on how Ascend manages that helps you understand how your data is being delivered in an incremental fashion. So I'm going to jump right into partitions in Ascend. What are they? So partitions in Ascend are individual batches of data within a component, and these are processed independent of other partitions. That is an important point because any transform logic that you have within your component is going to process individually from other partitions within that component. This is great when you have transformations that are doing any row-wise operation and works in most use cases. But when you get to something like an aggregation, like you want to get the max value of a column, then maybe you don't want to do partition-wise operations, and you want to do you want to carry out your transformation logic over the entire data set. So that's where repartitioning logic comes in with Ascend. The other thing that Ascend does is it collects a lot of metadata about your partitions. So this helps it better optimize computation for your partition, as well as the most efficient way to propagate data through your pipelines. The things that we collect are column statistics, which basically means the minimum and maximum values of each column within the partition, as well as we have information like partition runtimes and record counts per partition. We also have information about bytes per partition. All right. All this information is available to you within the Partitions tab. It is a super helpful view of your partitions within Ascend, so you can take a look at what they're doing. And we're going to actually jump over to the UI really quick. So I'm going to switch my sharing over to my Ascend pipeline. Cool. Yep, that's the right one. And I'm going to head into this ingest component, what we call a read connector. You can see that it says here we have 5 partitions. We default to the record view, but we could actually head on over to this Partitions tab to take a look at kind of how our partitions work. Each partition is going to have a partition ID. So you can see here that each of these is like a CSV file coming in from our source. Each partition also has a unique job ID. So this goes back to what I talked about, each partition being processed individually. This happens at the read connector as well. There is an independent, in this case, a Spark job that's running to ingest this data from S3. Then we also have the record counts. We have, if there are any errors, they'll show up here. We do actually show, if your partition, since partitions run independently, some partitions can error out while others don't. you can actually see that this partition errored out one time before a retry kicked in and it was able to recover. You can see logs and Spark job UI here. Like I said, this is a read connector, so it's ingesting data using Spark. You can see that Spark UI. You have the start time, the completion time, lots of other information. But what I did want to touch on is the column statistics that I talked about. So for example, one of the columns that we have within our component is this drop-off latitude, because this is cab rides data. So what we're storing in Ascend is actually the minimum and maximum values of that partition for that specific column. So in here we know that the specific partition has a drop-off latitude value that ranges from 0 all the way to 42. We're going to talk a little bit about later on how this helps with partitioning and how this helps with repartitioning specifically. And I'm going to jump right back into my presentation. Cool. Okay. So now that we have an understanding of just generally what partitions are within Ascend, we can take it all the way to the beginning of your pipelines and figuring out how partitions work at ingest. This is important because the way you read your data in, like the type of read connector you're using or the strategies within that read connector you're using, will determine what your partitioning starts off as. And obviously downstream, you can repartition, we'll get to that. But this really forms the basis of your pipeline's partitioning. Cool. So before we talk about partitioning at ingest, something that's important to understand is listing. If you've worked with Ascend, you notice that your read connectors will always go into what we call the listing phase. This is where Ascend is exploring your source data to actually look for any new or updated data, and that directly maps to any new partitions that need to come in. So at this point, when your component's in a listing phase, you're not doing any ingest. We're just exploring that data source to see if there's any new data. A pretty classic example of this is blob store. When we're running a read connector for S3 or ADLS or Google Cloud Storage, we're listing out the objects within that bucket or the ones that we've actually are interested in to see if there are any new files or if there's any files that have changed using their e-tags. This way, Ascend can then figure out which data is new and then pull them in as their own partition. Similarly, for something like an incremental database connector, Ascend will query the database to see if there's any new data and bring that in as its own partition. So key point here is just listing is when we're going out and looking for new data. And this ultimately also determines what the partitioning is going to be. So for example, in this green cab read connector, I'm listing, and once I'm done listing, you'll see that I go into parsing when I'm doing the actual ingest, and that resulted in 5 partitions. So if I head on over to the Ascend UI, a pretty neat trick, if you want to actually see like what happened with listing, you can go to the partitions tab and switch over to list. You can see that we ran this job, and we actually came up with 5 records as a result of this listing. That correlates directly to how many partitions we discovered that were new and how many partitions we had to actually re-ingest. All right. Cool. So then let's talk a little bit about how partitioning works with specific types of read connectors. Obviously, all these data sources are very different. And so how we ingest data from them is going to be different and will depend on the kind of configuration that you have. We're going to cover a couple of them, but if you have any specific questions about specific types of read connectors, either drop them in chat or find someone at Ascend to talk to through these, or check out our documentation. Cool. So the first one is blob stores. Probably the most simple one in that each file is going to be its own partition. This is the default behavior when you create a blob store read connector, so either S3, Azure Data Lake, or GCP Cloud Storage. This will be your default behavior. You can see that in the screenshot, each partition ID is just a single file within that NYC Taxi Green Cab folder. However, sometimes this isn't always the ideal solution. You don't always want one file per partition, because let's say you're ingesting log data and you're getting a new file every couple of seconds. You're going to end up with tens of thousands of files and tens of thousands of partitions within a couple of months, maybe a couple months or two. So in that case, you can use what we call object aggregation. That's a really powerful tool when working with blob stores because it lets you actually define the structure of your partitioning based on your files. We can actually jump into the UI really quick to see what those options look like. If I'm in my read character, I'm going to go and hit edit. I'm going to scroll all the way down to object aggregation, and I have a couple of options. So I'm going to talk about these briefly here. If you're interested in learning about these more in depth, feel free to come check out the Partitioning 201 talk that I will be doing on Friday. We'll go into depth of how to use these, how to best use them, what they actually do. But at a high level, what these do, adaptive will basically do kind of a best effort to aggregate your files into a certain partition based on some limit. Usually that limit is the number of bytes we can store within a single partition. You have the option to set these values yourself, or there are some defaults within Ascend. The other option is your leaf directory aggregation, which means that any subfolder that does not have its own child folder, we consider that a leaf directory, and we aggregate all those files into a single partition. Prefix regex match is actually probably the most useful and powerful one here because it really gives you fine-grained control on how you handle this partitioning. What it does is you specify a regex here that matches the prefix of your blob store objects, and then any objects that have the same prefix that matches this will get aggregated into their own partition. This is really useful when you want to aggregate your, let's say you have time-based folders, so you have like a year, month, day structure. This is really useful for then, if you want to, let's say, aggregate by month, you can use a prefix regex match for that. The final option here is reshape on metadata, which is we're not going to aggregate based on the name of your files. We're going to aggregate based on the last modified time. So you can pick the granularity here. Do you want it to be year, month, day? You can also, if let's say you don't want to use the last modified time, instead your file name actually has a date in it, you can extract that using regex as well. All right. So now that we're done with blob stores, let's run on to the next more common one, which is databases. With databases, we provide a lot of different replication strategies, and depending on which strategy you pick, your partitioning will be different. So the first case here that's most common is a full resync. This means that on each refresh, we are going to be ingesting your entire table and then getting rid of any previous partitions. So we're not storing any historical data. What this means is this means that your component will always produce one partition. Now, obviously, that's not always the case. We always, we deal with very large data, so we don't want to ingest the table each time. In this case, Ascend provides you the option to do incremental refreshes or incremental pulls. What this means is Ascend is going to only ingest new or updated records into a new partition within your component, and it's going to do that by figuring out based on an incremental column. So you as the customer will provide an incremental column, usually something like a last updated time column that basically represents when a record was last updated. And we will use that on the Ascend side to only pull in the new records. The way we do that is we're actually storing a cursor within Ascend that kind of keeps track of where we are within that table of how many which records have we already pulled in and which ones do we need to pull in. So for example, if you think about you do your first ingest of the entire table when you're doing incremental, you store the cursor value for the max value of last updated date. So you know that, okay, next time I refresh, I need all records that come after that. Then when we do the next refresh, what we're going to do is actually run a very similar SQL statement that's just, hey, give me all the records from my table where the last updated date is greater than this cursor value, ingest those into a new partition, and then update the cursor value based on the new max value of this last updated date. So the way this ends up working with partitioning is that you have a new partition for each refresh, only if that refresh actually results in new data. So there can be cases where you refresh your database refreshes, there's no new data, so no new partition is determined. Right, so a couple of other replication strategies that we have. One is table snapshot. This is really similar to full resync, The only difference being that this allows it allows you to keep historical partitions. So we are taking snapshots of your table over time on each refresh, and each of those end up as their own new partition. This is really useful for smaller tables where you don't have another means for maintaining any history for those tables as it changes. But as you would expect, if it's a fairly large table, it can rack up pretty quickly. The other option we have here is CDC, or change data capture. We can ingest change data capture logs from any source that supports it, and then we can use that in Ascend to actually bring a table up to its current state. This is something that is done manually through a transform. So in most cases, what we see is somebody using full resync to pull an entire table, and then using a CDC component to pull in that log stream, and then using a transform to apply the changes from the log stream onto the snapshot of the table. But when you have change data capture, we treat it as a stream. So each partition is actually just on each refresh, we just create a new partition with the latest CDC logs. So a couple of other types of read connectors that we work with, warehouses. Snowflake and Redshift work very similar to our other databases. They have the same replication strategies, full resync, incremental, snapshot. So the partitioning there works pretty much the same. For BigQuery, actually, we support native BigQuery partitioning. So if you have a partitioned or a sharded table, we respect those partitions. If specific partitions in your BigQuery change, then we re-ingest just that partition. For queues, these work very similar to the CDC stream we talked about, in that every time we refresh, we just create a new partition with the latest records or messages that have arrived. All right. So we've talked about ingest. We've ingested our data into whatever partitions we need them to be in. And now we're at the point of transforming our data. So how do we manage these partitions at transform level? So something I keep kind of talking about is how individual partitions are processed, which means they're processed individually of each other. The reason I do this is because sometimes there is confusion of when I write a PySpark transform or I write Spark SQL, BigQuery SQL, what is that actually applying to, and how does that work with partitioning? So the way to think about it, if your component is going to have multiple partitions, so let's say it's like a map 1-to-1, it's a full reduction, or it's a map 1-to-1, or it's a repartition, your SQL or your transform logic is going to run independently and separately for each of those partitions. So for PySpark and PySpark SQL, what that means is that each partition is submitted to the Spark cluster as its own Spark job. In BigQuery SQL and Snowflake SQL, we are sending a separate query down to your data plane, so either BigQuery or Snowflake, for each partition. Awesome. So now that we understand that, we can take a look at how to start manipulating these partitions to best meet our needs. We have three options with a transform on how you can actually repartition your data: full reduction, map partitions 1-to-1, or repartition by a date-time column. One thing that I will note here that is, I think, pretty important to understand is repartition is what we consider a partition operation. So it's an operation that occurs on the partition itself, not the specific records. Other similar partition operations are partition filters, partition unions. And the thing to know about these is that all partition operations happen in a component before any of the transform logic is actually executed. So for example, if you are repartitioning, your Ascend component or the Ascend job will first repartition your data into those specific partitions, and then it will run the transform logic on those partitions. We'll be talking, not to plug it again, but we will be talking about this more in depth in the Partitioning 201 talk on Friday, so feel free to check that out. So let's take a look at the specific examples of how to do repartitioning, starting with full reduction. Full reduction is pretty simple and self-explanatory. It takes all the partitions in an upstream component and reduces them into a single partition. What that means is when you're writing transform logic, you should write it as if the input that you're referencing includes all data from the upstream. So for example, if you see in one of these screenshots, you're referencing the upstream table by grabbing the first element from the input 0. In a full reduction case, that means that the first element of the inputs array is actually the entire data set of the upstream. Yeah, so this is super useful when you want to carry out any logic that requires, going across all your partition data or all the upstream data. So anything that's like an aggregation or a window function. Only caveats here is that obviously it can be computationally expensive since you're bringing all of your partitions into a single one and running transform logic on it. You also end up losing any kind of incrementality you were doing. So for example, in our case, if these first two partitions that we see on the left were to reprocess, but the third one did not reprocess, that still means that our full reduction component will reprocess. The actual process of repartitioning data, though, which is the act of taking the multiple partitions, turning them into one, is not a computationally expensive process at all, since we're just taking all these partitions and mapping them to one. The reason this is important to understand is that as we get into something like repartitioning by date time, that process can actually get a little bit more computationally complex. All right. Mapping one-to-one. This is actually probably one of the most common examples of how partitioning works. It's usually people's default. What's so great about it is that we're just maintaining partitioning from the upstream. This is super useful when your data is already partitioned the way you want it to be. It also means that you maintain any incrementality from the upstream. So if only one partition in the upstream reprocesses, only one partition in your component is going to reprocess. The only thing to think about here is that when you're writing any transform logic within your component, you're actually referencing a specific partition in the upstream. In most cases, you don't really need to think about this because your transform logic will work the same regardless of if it's map one-to-one or if it's full resync. But if you do something like a aggregation, like the aggregation will run for each partition. That is useful to know because let's say, for example, you have 10 partitions in your upstream and your component, and you do a max, hey, I want the max value of a column, select max of column from my upstream. You're going to actually end up with 10 records in that component, 1 record per partition, because it ran that max for each of those partitions. That's just one of those things that kind of sometimes catches people off guard when they're working with components with multiple partitions. So finally, we get to repartitioning by date time column. When you actually want to change the partition structure of your data as it's flowing through send. It can be pretty tricky to get right or to understand, but it's super useful because oftentimes when you're reading in data, even with all the tools Ascend provides, your data might not be in the partitioned the way you want it to. The way this works is that Ascend will ask you for a column you want to repartition on. So it has to be a date time column. And then after that, you give it a granularity. So I want hourly partitions, daily partitions, monthly partitions. This process can actually be a little bit computationally heavy. So we would want to be careful just because Ascend needs to shuffle records between partitions. But as I mentioned before, we had talked about column statistics. Those column statistics, those min and max values, actually make this process a lot smoother and a lot easier. So I think this is plug number 3 for Partition 201 talk, but really get into the nitty-gritty of that stuff over there. So let's take a quick look at how these work in the UI. So what are you going to actually see in Ascend? So if I share this, get out of my read connector. Actually, I don't want to get out of my read connector. I want to head over to the partitions tab, discard my changes. You can see that in my component, I have 5 partitions. Each partition is 1 file. So when I head downstream, I've made 3 components, 1 for each partitioning type. Simplest one, reduce partitions 1-to-1. We have a single partition here. And something really interesting, actually, you can take a look at is if you head to the partitions tab for the single partition, you can see that you can actually scroll over and see how many partitions we had to read in to get the data for this partition. This really gives you a good idea of when you're partitioning, what is the actual data that this partition has to process. Similarly, if we head on over to map partitions 1-to-1, and we head on over to the partitions tab, in this case, it's the same thing. We have 5 partitions coming in from the upstream. And if we head on over to the partitions read, each partition is just reading one upstream partition, so that makes sense. And then if we head on over to repartition by datetime, you can see I somehow ended up with 91 partitions. So the reason that that happened is because I decided to repartition on this LPEP pickup datetime, and I chose a granularity of 1 day. My data is probably spread across about 3 months, so that checks out roughly. I think the math is kind of correct there. But if I actually head on over to the partitions tab for these, we can actually see how that repartitioning worked. So if I head on over to the column statistics for the LPAP pickup datetime, which is the column that I repartitioned on, you can actually see the range of values within each of these partitions correlate to those, let's say, buckets of days. So for example, this partition has all the data for March 10th. This one has all the data for March 25th, March 21st, so on and so forth. The other interesting thing to take a look at here is that we went from 5 partitions in the upstream to 91. So in most cases, that was, each of these partitions have to just read in one partition of data because the data for that date is sitting in just one of those upstream partitions. But in some of those cases, actually, we can see that some of these partitions had to ingest 2 partitions from the upstream, which probably tells us that the data for this partition was sitting in 2 of those upstream partitions. That's just kind of an example how Ascend uses those column statistics to determine where your input data is coming from and where you need to look, without actually having to scan the entire data set when reading in that data. All right, I'm going to switch over back to my presentation. And let's finally talk about partitions when writing. Now, partitions when writing will obviously vary from the type of write connector that you're using, and the strategies differ, but there is kind of a basic concept on how we maintain partitioning and incrementality when writing data out. So in this example, we're going to be taking a look at Blobster and Snowflake specifically, just to see how we handle that. So the way the Ascend actually manages this is with something called the Ascend partition ID. So when we're writing the data out, Ascend will maintain an Ascend partition ID, which allows us to identify partitions in the destination. So we can actually come up with a correlation between the partitions we see in Ascend versus what's already been written out. In this example, you can kind of see on the left, we have S3. We have a bunch of metadata folders, each of these with a UUID that represents the Ascend partition ID. And in Snowflake, we have a query that one of the tables we wrote out just has a column for Ascend partition IDs. How is this Ascend partition ID calculated? It's actually taking the upstream partition SHA and then SHAing the write connector configs and combining those at a very high level. If you know anything about Ascend, you know that we love our SHAs. This is no exception, but this does some interesting things because it means that, let's say a specific upstream partition changes, just its upstream partition SHA changes, that means that only the Ascend partition ID for that specific partition is going to change. So Ascend will know, hey, I only need to update that specific partition. However, if you change some configuration in your write connector, you end up changing this write connector config SHA for all your Ascend partition IDs, so all of them need to reprocess, which makes sense because let's say you change something like the table that you're writing to, and you want that obviously to apply to all partitions. Changing that write connector config changes the SHA, changes the Ascend partition ID for all partitions, and so all partitions get written out. So in the Blobster example, we manage these partitions with Ascend metadata files. These files include, you can see they have the Ascend metadata prefix, but then they also have the Ascend partition ID. If we were to click into one of these files, you can see that for a single file, we do keep track of the parts in that file. So for example, which data files actually belong to this partition. In this case, it's just one Parquet file. And then within that directory we're writing to, you'll actually see the data files with the Ascend partition ID kind of prefix at the beginning of it. For Snowflake, it's a lot simpler. All we're doing is adding a column to the table that we're writing to with Ascend partition ID in it. And that's how we reference specific records for that partition ID. It works similarly for when we're writing incrementally to databases as well. So when we're writing data out, since we have a way to correlate the partitions in Ascend with the partitions that are being written out, we can actually do some pretty smart things of figuring out, okay, what is the difference and which partitions do I need to add to the destination and which do I need to pick up since they're no longer valid. All right, final plug for this. I think it's number 5, maybe. But Friday, I will be doing a partitioning 201 talk where we'll be kind of deep diving into some of the more advanced ways you can manage partitioning. The object aggregation I mentioned earlier, we're going to go deep on that. We are going to be taking a look at how do you manage partitions when you have multiple input components with multiple partitions, and you don't want to end up with a Cartesian product of partitions that blows up the number of records. There are super useful tools like partition union and partition filtering that we'll be taking a look at. And with that, it's going to be time for our Q&A.
All right. That was awesome, Shayaan. Thank you so much. So let's get started in Q&A. First question is, how do people generally handle CDC data within Ascend?
Yeah, that's actually a really good question. So in Ascend, how we ingest CDC data, as I mentioned, is just that stream of data. So we're just getting the raw CDC logs from whatever your source is. So for example, if it's, I believe Postgres has CDC, if it's Postgres, we're ingesting that. So generally the pattern that we see is people will use a full resync Postgres read connector to ingest just the current state of that table at a given point in time. And then they'll create a separate read connector for ingesting the CDC streams. So now you have your snapshot, your starting point, and then you have the change log that you want to apply to that snapshot. So you'll create a transform downstream that all you do is take that CDC logic and apply it on top of the snapshot that you have, so you can get the latest state of that table.
Awesome. All right. Next question. How are partitions actually stored within Ascend?
Yeah, that's a good question. So that actually depends on the type of environment, or so we call the data plane that you are running. If you're not super familiar with the backend of Ascend and how things work, we have what we call a storage layer. We have a data plane which has a storage layer and a compute layer. So the storage layer is where your data is actually being persisted, and the compute is what's handling the processing of that data. There are a couple of different data planes depending on what your environment is using. We have Snowflake, BigQuery, Databricks, and then we have a Gen 1 Spark environment. For most people who have been customers for a while, who have Gen 1 Spark environments, your data is sitting in Blob Store for your account. So depending on what cloud that you're deployed in, it'll either be GCS or it'll be S3. You'll see that there are some buckets deployed there that is actually storing your records. I believe it's called it's either called the records bucket or a fragments bucket, but it is just sitting in Blob Store. And then the partitions are basically, there's some work in the backend to map partitions to specific folders within that. That's not super visible to not super human readable, but it makes sense to the Ascend scheduler. For our data planes that are Snowflake, BigQuery, or Databricks, we will have tables for each component. So for example, for Snowflake, if you have a Snowflake component with 5 partitions, we have a Snowflake table for that component. And then that, I believe, also has a column that says Ascend partition ID. And that Ascend partition ID basically associates each record in that table to one of your Ascend partitions.
Perfect. OK. And then final question, how do I customize partitioning when writing to Blob Store?
Awesome. Yeah, so there are a couple of ways to do that. We have some options. I'm going to share my tab so we can take a look. So let's head on over to one of the write connectors that I set up. So like I said, when you have, just by default, you kind of Ascend manages that partitioning for you based on the metadata. However, there are some options to manage the partitioning when you're writing data out. One of these options is what we call a partition interpolation template. So if your data upstream is partitioned on a specific date time column, then you can use that within this to actually create subfolders where your subfolders based on your partitioning. So you can actually see from the tooltip, one of the examples here is that if your data has a upstream column called event_ts, you can specify a pattern here such that every partition of data will go into a separate subfolder. So this gives you some more fine-grained control on what you're trying to do. If you really want to control exactly, how your subfolders are managed, how your subfolders are managed, how your files are named, for example, then we also have the option to write data out with custom Python, so what we call a custom function. So within the write connector, you actually have the option to specify a function to write data out. And we provide a lot of cool interfaces here for actually doing that. So we provide a async file system interface to actually treat your blob store location as a file system you can just write to. We provide a Spark session in case you want to use Spark. What's useful here is this data provider class. This is an Ascend class that actually stores all your upstream data coming in. And you can use that to do some pretty interesting things. If you scroll a little bit down on this documentation, you can see what that data provider class actually looks like. If you call the data method for it, you can actually get all the data from the upstream, and then you can do whatever you want to write that data out. But you can also call this partitions, and this will return an array of partition objects. So you can get individual partitions from the upstream. This partition class also has a couple of methods. It has the semantic SHA. This returns what we call the semantic SHA for that partition. These semantic SHAs are kind of similar to what we saw with the Ascend partition ID, where they're a function of your input data SHA and the SHA configuration of your write connector. And then for each partition, you can also get that data. So if you really want to control how each partition is written out, you can call this function to get each specific partition, and then for each specific partition, access its data. One of the examples we have here is we have some upstream data that we want to write out to, we're writing this out to S3, but we want to be able to partition it based on, down to the minute. So we're using, I believe, PyArrow for that. And all we're doing is getting the data from the upstream, converting it to pandas, pandas data frame, and then using write to data set to write this out to our file system. So with this custom approach, we do give you a lot more control over exactly how you write your data out. Cool.
Great. All right. Thanks so much, Shayaan. I'm going to do one last plug. Don't forget, Shayaan will dive deeper into partitioning at scale on Friday with Partitioning 201 at 9 a.m. Pacific.
Awesome. Thanks so much, Carissa.